Hello, this is a continuation of our study of acid-base equilibria in Chapter 14. Today we are going to talk about an analytical application of acid-base chemistry known as acid-base titrations. From acid-base titration data, we're also going to draw what's known as pH curves. So we're going to basically calculate a bunch of data for different types of acid-base titrations and then plot them to generate pH curves. So before we get into the nitty-gritty details and the calculations, I want to really understand what acid-base titrations are. The first thing, which is very important, is that for an acid-base titration, you must have a reaction that goes to completion. What that means is that at least one of the reactants must be strong, either a strong acid or a strong base, to drive that reaction forward towards products. So because of that, we have only a limited number of types of acid-base titrations that we can have. You can titrate a strong base with a strong acid, or vice versa. You can titrate a strong acid with a strong base, but in any event, both of the components can be strong. Or you can titrate a weak base with a strong acid, or you can titrate a weak acid with a strong base. So these are the three combinations that will allow for a titration. So any of these combinations will permit a titration. One very important concept when it comes to titrations is the idea of an equivalence point. And you've really even thought about equivalence, even going back to General Chemistry 1. Equivalence is when the number of moles of the strong component that you're adding, so this could be either strong acid or strong base, that are added are going to be exactly equal to the number of moles of either base or acid, it could be strong or weak depending on the titration, present in your analyte. The analyte is just the sample that you are titrating, the sample that you are analyzing. So let's think about the equivalence point using what we know so far about acid-base chemistry for strong acid, strong base titrations. So for strong acid, strong base combinations, what would be the pH at equivalence if we're titrating one with the other? Let's look at an example to try to answer this question. Let's take the classic strong acid, HCl, and the classic strong base. And imagine we're titrating one with the other. It could be either way. The equivalence point is defined at the point at which both of these are stoichiometrically balanced, so that the number of moles of one equals the number of moles of the other. Now, since these are strong, the reaction goes to completion. And what happens here, you've written down reactions like this back in general chemistry, is that the acid donates its proton to the base to make water, and you have these spectator ions floating around in solution, the non-acid sodium and the non-base chloride. This reaction goes to completion because both of the components are strong. So now, if this reaction goes to completion, what do we have in solution? Well, we have water, and we have spectator ions, a non-acid and a non-base, sodium and chloride. So what is the pH at equivalence? Well, since these don't have acid-base properties, and this is just pure water, the pH at equivalence must be 7, because this is a neutralization reaction. And this is going to be true for any strong acid, strong base titration. For any strong acid, strong base titration, because at equivalence you just effectively have pure water. So back in Gen Chem 1, you called this a neutralization reaction. which is another word for a strong acid, strong base reaction. So literally in a titration of a strong acid with strong base, at equivalence, you have achieved neutralization, and the pH should be 7. Let's think about the titration of a weak base with a strong acid. What would the pH be at equivalence? So what about the titration of a weak base with a strong acid? What is the pH at equivalence? Okay, let's think about an example to illustrate that point. So let's take as an example classic weak base, ammonia. So ammonia is a weak base, and let's react it with a strong acid, hydrochloric acid. Now, hydrochloric is a strong acid, so this goes to completion. This goes 100% in the forward direction. And that strong acid is going to donate a proton to the weak base so that I get ammonium and chloride as my two products there. So when those two reactants, ammonia and hydrochloric acid, are perfectly stoichiometrically balanced, what do we have in solution? Well, looking on the right side, we just have created, the weak acid, ammonium, and the non-base, chloride. So that ammonium is going to dominate the pH in solution. Okay, in the solution. So what should the pH be? Therefore, the pH is going to be acidic. It's going to be less than 7 because you have a weak acid in solution at equivalence. Okay, so the pH is going to be less than 7 at equivalence. And this is going to be true in any titration of a weak base with a strong acid. So any strong acid weak base titration is going to give you a pH less than 7 at equivalence because you simply are going to have the weak acid created in solution from that reaction. Let's now just quickly to tie this up, look at weak acid titrated with a strong base. A weak acid titrated by a strong base. Let's give an example of that. Let's take acetic acid and titrate it with the strong base sodium hydroxide in aqueous solution. Since sodium hydroxide is a strong base, this reaction is going to go to completion. And the strong base is going to deprotonate the acetic acid to make acetate and water. And you'll have a spectator ion floating around in solution as well. So if we look at what's present at equivalence, you are going to have a weak acid, water, my bad. That, of course, is not a weak acid. That's a weak base. Acetate is a weak base. You're going to have a non-acid, sodium, and then you just have water, which, of course, is neutral. So that means that at equivalence, strong base, weak acid titration will give a pH of greater than 7 because weak base controls the acid-base chemistry in the solution. So I hope that makes sense to everybody. Just to summarize what we have talked about thus far, the pH at the equivalence point for a strong acid, strong base titration is going to be 7, because what you have in solution at equivalence is 2 non-acids or non-bases and water. For a strong acid, weak base titration, your pH is going to be less than 7 at equivalence, because you are going to have 1 non-base plus 1 weak acid in solution. And finally, for a strong base weak acid titration, at equivalence, your pH is going to be greater than 7, because you are going to be left with 1 non-acid plus 1 weak base in solution at equivalence. Okay, so these are just some qualitative concepts about acid-base titrations to introduce you to the idea. In the next lecture, we're going to actually do calculations for an acid-base titration and generate our first pH curve. Thank you very much for listening.